Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my pleasure to introduce Hitesh Balani, who's visiting us here from Cornell. He's a student of Paul Francis. He'll be talking to us today about his work on the router table space exhaustion and what can be done to fix that. He has other work in extensive work in internet measurement, working with the DNS and Anycast problems, as well as work in top-down management of IT infrastructure and networks. So thank you very much for joining us, and Hitesh, please take it away.
Thanks, Dave, and thank you for having me here. Before we jump into the technical details, I wanted to give you a brief overview of the kind of work I do. And I figured what better way than a wordle of my research statement. Now, I'm sure you've all heard this argument in one form or the other, that the explosive growth of the internet over the past decade has meant that many of the original assumptions underlying internet design no longer hold true. This has led to a plethora of problems, which is good for us because there's work to be done. However, there's a flip side to the story. The success of the internet has meant that you can't really go out and say, well, let's take this protocol out and put this new one in, and voila, the problem goes away. Throughout my graduate career, I've tried to stay cognizant of this ground truth. And I've really strived to strike a balance between two competing urges regarding my research. On one hand is the freedom of doing blue sky research, openly questioning internet design in the face of new needs and challenges. For instance, as Dave mentioned, as part of my dissertation, I look at the problem of network management. And I argue that networks today are so difficult to manage because the internet was not designed with manageability in mind. So what I mean by that is protocols today tend to expose their internal bells and whistles. And both humans and management applications are sort of expected to understand these low-level parameters in order to be able to manage the network. Hence, we proposed a new network management architecture called Complexity Oblivious Network Management, or CONMAN for short. As part of CONMAN, we precisely define the kind of information that should be exposed by protocols in order to make them amenable to management. All these protocols were implemented and deployed on a real testbed, and what we found was that the resulting testbed was much easier to configure. Further, when things went wrong, you could debug and diagnose the network faults in a structured fashion. So overall, it was a lot of fun showing that this complex problem of network management can be tackled through such an invasive approach. Question?
Are you going to give us more detail later in the talk about how you demonstrate this?
On network management? Yeah. No, the talk is generally about my routing work, but if you're interested, I'd be more than happy to speak to you about the network management stuff and my vision there. Okay. On the other hand, I do want my research to have real impact through solutions that are immediately deployable. Now, this may seem to contradict what I said earlier when I claimed that a lot of these network problems arise due to a mismatch between design and use. And I still stand by that. However, what I have found is that in many cases, simply by focusing on a subset of the given problem space, you can come up with a solution that does not require wholesale change. And this is a recurring theme in my work, a trick that I use over and over again. And these are not just point solutions. As I'll explain later, these can actually serve as small incremental steps towards the eventual solution that you'd like anyway. So there's a clear progress path between what can be done today and where you'd like to be 10, 15 years from now, which I think is pretty neat. To give you a few examples, I have worked on how to deploy IP Anycast, which is essentially a network layer service discovery mechanism in a practical and scalable fashion. So effectively, I built the service. I deployed it at 7 servers across the internet, which included BGP peerings with various ISPs. And I've maintained this testbed for the past 4 years, and it has also been used by other researchers for active routing experiments. On a similar note, I came up with a minor modification to the caching behavior of DNS resolvers. And I showed that this can substantially mitigate the impact of denial of service attacks on DNS. Now, this was a very, very trivial idea, but I'm still very proud of it because at the time when these papers were published, a lot of people were proposing novel peer-to-peer architectures for DNS. Now, that's all great work because DNS does suffer from severe problems. What I showed was that if you focus on the specific problem of flooding attacks, you can come up with a solution that does not require infrastructural change. And as it turns out, there is a connection between this simple idea and the other clean slate proposals that I just mentioned. And finally, there is my more recent work on routing scalability, which is what the rest of this talk is about. So we'll be switching gears here a little bit and moving on to the technical component of the talk. Now, I'm sure many of you must have heard about the growth in the internet routing table, and you must have seen this graph. And you can see that the growth has been rather steep over the past few years. What is more worrying is that this is probably going to get worse in the near future. This is because as the IPv4 address space runs out, more and more small prefixes will be advertised, resulting in a larger routing table. And if, lo and behold, the IPv6 deployment takes off the ground, we could end up with a very bloated routing table. Now, this routing table specifies how a given router should forward data packets. And so routers need to maintain this in fast memory as part of something called the forwarding information base, or the FIB for short. And I'll explain how that works later. Hence, a larger routing table means that ISPs need routers with more and more FIB space. Given this, there are two questions that come to mind. The first of which being, why is the routing table growing so rapidly? And I'll comment on that very briefly. The scalability of the internet's routing system relies on hierarchy, which in turn requires that the addressing of ISPs on the internet be in line with the actual physical topology. So if you had a nice figure like this, wherein the address space of any given node is a subset of the address space of its parent, you'll get good scalability. For instance, if you look at the routing state at ISP A, it only comprises of other top-level ISPs and its immediate children, a small amount of state. However, the growth in the internet has meant that this nice picture is no longer true. In the figure, I've shown how site multi-homing, wherein a given site connects to multiple upstream ISPs, can lead to a mismatch between addressing and topology. And there are multiple factors that can lead to this. But the point here is that this mismatch between addressing and topology is the root cause for the rapid growth in the internet's routing table. The second question that I'm often asked is, so what? Why can't you throw more RAM at the problem? And that's exactly what has been happening. Every few years or so, router vendors come out with a new generation of routers that have more memory and more processing power. And I'm not arguing that they can't keep on doing this forever. However, the problem is the scalability properties of this FIB memory. On the technical side, there's a concern about the amount of power these massive chips consume, not to mention the concomitant heat dissipation problems, which are especially relevant in the kinds of locations where these routers are housed. Further, off-chip SRAM, which is what is commonly used for router FIB, is a low-volume component that has been shown to not track Moore's law. So the cost curves are not in our favor. And what I mean by that is a larger routing table reduces the cost effectiveness of ISPs because the price per byte forwarded increases. And of course, there's the cost of actually upgrading the router because it ran out of memory. However, in spite of all these reasons, I have to admit that FIB size is a contentious issue. There are people who think FIB size is an important problem, and then there are the non-believers. As a matter of fact, in one of my own papers a few years ago, I had argued that it is technologically feasible to add more state to routers. And I still stand by that. And while my thinking has evolved over time, the stand that I'm going to take in this talk is that given the technical and the business implications of FIB growth, you can't be sure of the criticality of the FIB growth problem given existing data. Looking ahead, there are several very good reasons why you'd want a smaller routing table. And of course, these are speculative in nature. But what really sealed the deal for me were recent events and discussions with ISPs and operators. And I'll give you a quick example. ISPs in Australia have already started filtering out small prefixes, mostly /24s, which is the smallest address block that you can advertise into internet routing. This is because these ISPs don't want to upgrade their installed router base, which is scary because it implies that parts of the internet may not have reachability to each other. So hopefully this quick anecdote convinces you that ISPs are concerned about the FIB on their routers. And they're actually willing to undergo some pain to extend the lifetime of their installed router base, which is good for me because there's a specific real problem to solve. Question?
When ISPs do that kind of filtering of this /24s, does that really mean you don't get reachability, or does it mean you just get inefficient routes?
It could mean inefficient route for the most part, but it could mean to non-reachability. So they're not just filtering out /. I don't think there has been active study. I've done some random hacks or measurements, and it seems that in some cases there's a decent amount of inefficiency because you're not just throwing the /24 away. You're ensuring that there is some super prefix such that you have a /16 and you're throwing the underlying /24s away. But because of multi-homing, in some cases, it might be the case that you don't even get reachability. And I've seen a couple of instances of that. But I don't think there has been any measurement, systematic measurement of that. Albert?
Curious, who is the Australian ISP?
This was a PACNAR mailing list, and they had mentioned several Australian ISPs. I don't have specific names. Right? Okay, so this is good because there's a specific problem solved. And motivated by this, we propose virtual aggregation, or ViAggre, a configuration-only approach to shrinking the FIB on ISP routers. By configuration only, what I mean is that ViAggre does not require changes to routers and routing protocols, and it can be deployed independently by any ISP on the internet today. In case you were wondering, I did not come up with that name. The credit or the discredit for that goes to Brad Karp at UCL. Also, it's ViAggre with a V, not with a W, as it may sound when I say it, because my V's and W's are messed up, and a joke doesn't really come out with my pronunciation, but anyway. But well, this talk focuses mostly on the research component of ViAggre. But I do want to point out that these features have allowed ViAggre to have real-world impact. For instance, there's ongoing standardization effort in the IETF for ViAggre. This is spearheaded by Huawei, the largest router manufacturer in China that provides equipment to more than 70% of the top telcos. As a matter of fact, Huawei is also implementing ViAggre natively into its routers. And I'll explain later what the advantages of such an approach would be. But the point here is that this possibility of real impact is what is so exciting about Dirty-Slate research, at least from my point of view. The basic idea behind ViAggre is really simple. Today, every router needs to maintain the entire routing table. In ViAggre, we allow the ISP to divide the routing table into parts such that individual routers only need to maintain routes to a few of these parts. And so you get a shrinkage in FIB size. And I'll explain that as we go along the talk. So the way I've set up the rest of the talk is that I'll begin with some basic information on internet routing, which I'm sure most of you know anyway. It will help me come up with a crisp problem statement, and it will help me place this work in context. So, internet routing. Internet routing is domain-based, wherein the domains are independent autonomous entities. These could be ISPs like AT&T and Sprint, and enterprises like Microsoft, and university networks, and so on. Such domains lend themselves nicely to a two-tiered routing architecture, wherein you have intra-domain routing to establish routes within a domain, and inter-domain routing to establish routes between domains. On the internet, BGP serves as the de facto inter-domain routing protocol. And BGP is what the rest of this talk is about. Moving from this very high-level view to the innards of actual routers, what I've shown here is a router that is connected to two other routers. At the top, there is a root processor, which is responsible for the router's control plane tasks. This root processor maintains what is effectively a database of routes that it obtains from other routers. This is known as the routing information base, or the RIB for short. And it's generally maintained on slower memory. For instance, DRAM might be used. On the other end, we have the line cards, which are responsible for actually sending and receiving the packets. These line cards maintain a table of routes based on which they forward these packets. And as I mentioned earlier, this is known as the forwarding information base, or forwarding table, or routing table, or FIB for short. Obviously, the FIB needs to be accessible at line rates. And so it's generally maintained on fast memory. For instance, off-chip SRAM may be used. And here, I've shown how packets might come in through one line card and be switched onto another line card. So two important things to note. RIB resides on slow memory. FIB resides on fast memory. Given this basic routing information, we can take a look at the scalability problems afflicting internet routing. As I mentioned earlier, a larger routing table has led to concerns regarding FIB growth. Beyond this, there are concerns about rib size problem, routing convergence, and all this has been known for a while, which shows up in the massive amount of work done in this area. And at a very high level, there are approaches that argue for separating edge networks from core networks. There is geographical routing. There's been a whole lot of work, especially in the theory community, on compact routing. There are elimination approaches. And without going into any details at all, the common theme here is that all these approaches require architectural change. I don't mean that in a bad way, because I do realize that a lot of these problems arise from the way internet routing works. And so some change is in order. However, this very need for change has meant that none of these approaches have seen any deployment. Frustrated by this lack of deployment, I started wondering if you can do away with the need for change by focusing on some of these problems. Guided by this, in ViAggre, we tackled the FIB size problem in an incremental fashion. And as it turns out, our current techniques can also help with both rib size and routing convergence. So again, we have this notion of achieving deployability by narrowing down our focus. So in this talk, I'm going to focus mostly on FIB size, and if time permits, I'll comment on how ViAggre can be applied in a more invasive fashion to tackle the entire routing scalability problem space. And with that big picture in mind, we can delve into the ViAggre design question.
So you showed us how the advertised BGP table grows over time. Can you tell us how the FIB grows compared to that?
Say that again, please.
How does the FIB grow compared to the growth in the routing table size?
So the routing table size that I showed was the actual FIB. So it's the FIB size, the global FIB, or there are routers in the default free zone, which routers that can't use default routes, and that when I said internet routing table, that essentially meant the FIB size in the core of the internet. I didn't want to use the term FIB at that point of time because I hadn't introduced it. Obviously, the rib can be much bigger because it depends on the number of peers you have and other factors. So that graph was for the FIB on the core of the internet. Okay? So ViAggre design. And in the figure here, I've shown an ISP with 3 POPs, or points of presence. These are routing centers in different geographical areas, and a few routers in each POP. Today, as I mentioned, each of these routers needs to maintain the entire routing table. In ViAggre, we allow the ISP to divide the IPv4 address space into parts. Here, I have divided into 4 parts, which are color-coded. Each of these parts can be represented by a /2 prefix, which I'm going to refer to as a virtual prefix. Now, I'm assuming that people are aware of the slash notation. Since I have 4 parts, I only need 2 bits to represent them. And so only the 2 higher order bits of the IP address are relevant. Everything else is masked off. And that's what /2 means. Beyond this, the ISP assigns its routers to these virtual prefixes. So the 2 green routers are assigned to the green virtual prefix, or they're aggregation points for the green virtual prefix. What this means is that these routers are responsible for routes to any prefix in the green part of the address space. And you can imagine how this would ensure that, on average, every router maintains a quarter of the internet's routing table. Of course, this assumes that the prefixes are distributed uniformly across the address space, which is obviously not true for the internet. However, you can choose these divisions such that the distribution of prefixes across them is relatively uniform. Now, this basic idea of dividing the routing table can be achieved in a number of ways. For instance, you could change the routing protocol to do this. However, we wanted a deployable system. And so a key design challenge was, how do you achieve this without changes to routers and without requiring external cooperation? Further, once you divide the routing table, how do packets flow through the ISP's network? Because routers now only have partial information. So in the next part of the talk, I'm going to elaborate on ViAggre design by answering these questions in order. First up, the control plane design. In ViAggre, we need to make sure that the forwarding table on any given router. Question?
Yes. So is there only one router per point of presence in this picture?
This is a simplified picture, and that's what is misleading here. So in a typical deployment, and I'll get to that later, a typical POP has 20, 30 routers. And so you would want to make sure that there are 2 routers, or at least 2 routers responsible for every color in each POP for things like stretch and redundancy. And I'll get to that in like 4 or 5 slides from now. Okay? So in ViAggre, you need to make sure that the forwarding table on any given router contains only roots for the prefixes that is aggregating. So the blue router should only contain blue prefixes, which is a problem when you consider interaction with external ISPs. In this case, the external router is advertising the complete routing table to the blue edge router, even though it's responsible only for blue prefixes. And so we need some mechanism of selectively inserting roots into a given router's forwarding table. We came up with two mechanisms to achieve this. As it turns out, one of them doesn't really work in practice. The performance overhead is too high. So what I'm going to do is that I'm going to explain both the mechanisms at this point of time. And once we go into the performance evaluation section, I'll explain why one works while the other doesn't. The first mechanism, or design one, takes advantage of a router feature that we call FIB suppression. With FIB suppression, you can configure a router to only load a subset of its RIB into its FIB. So in this case, the blue router gets the entire routing table, loads this in its RIB, and only loads the blue roots into its FIB. The advantage of this scheme is that the ISP does not need to modify its internal routing setup at all. Everything remains the same as today. Every router gets the entire routing table and selectively inserts roots into its forwarding table. The disadvantage is that there is no RIB shrinkage at all, because every router still needs to maintain the complete routing table in its RIB, which is the slow memory. So that's the disadvantage. Question?
The contention is that you don't change your hardware for this.
Yes.
Is that true?
We don't change the hardware and the software for this. As it turns out, existing routers have this capability of putting entries, selectively putting entries from the RIB into the FIB. Whether that's practical or not, I'll show you later that it turns out to be not practical. That's the catch here. But there is a second approach that does end up working. Okay?
I mean, the RIB is something you're storing in DRAM, right?
Yes.
Presumably only a few gigabytes for the whole internet,
yes.
Right? And so we're talking about gigabytes of DRAM that cost hundreds of dollars in, so is that a problem?
No, the DRAM or the RIB size is not a problem per se. What it turns out, and I'll show this later, that reducing the RIB, which the second design does, not this design, actually helps out with internal routing convergence. What ends up happening is that you're sending less number of routes to your routers because the RIB size is smaller, and that helps with internal routing convergence. So the memory cost on the RIB side is not important. Okay? I should have clarified that. The second design is slightly more invasive, and it offloads the task of maintaining this complete routing table onto machines that are off the data path. That is, machines that don't forward data packets. As it turns out, ISPs already use such machines for scalable internal distribution of BGP routes, something called BGP route reflectors. So without going into any design details of how route reflectors work, in this design, the external router, instead of advertising routes to a blue edge router, it has a peering to a POPs route reflector. And it is the route reflector that selectively forwards these advertisements to the ISP's routers. So the blue router gets only the blue prefixes, the green router gets only the green prefixes. And these routes are propagated to route reflectors in other POPs and so on. Question?
So if you have route reflectors, why don't you run another routing algorithm at the third level of hierarchy on top of BGP to solve this problem?
So a lot of people have proposed things like RCP and 4D, where you separate this logic from the actual data plane routers, and you can take advantage. If you notice that the route reflector here is similar to a decision element in 4D and an IRSCP, and you'll notice that the solution I come up with, for instance, RCP was focusing on routing convergence. 4D was focusing on networking management. I'll come up with a solution that is pretty similar and compatible with those models. So you can use ViAggre in the context of those models to achieve reduction in routing table size. So I'll answer your question once I've explained my process, and I'll explain why ViAggre fits into the RCP model and what would happen if you had the flexibility of changing routing protocols. Question? Yeah.
Do you have perspective on how many IBGP configurations do these route reflectors?
How many IBG configurations do these route reflectors have?
Yeah. How many IBGP configurations inside ASs actually don't use route reflectors?
Oh, how many IBGP configurations inside ASs don't use route reflectors? As far as I know, and maybe people here might be able to, as far as I know, most tier 1 ISPs and tier 2 ISPs use route reflector-based configurations, so we should be safe in that aspect.
So obviously, the route reflector does need enough SRAM, DRAM, whatever.
DRAM, because it's not on the forwarding path. Yeah. Okay. Yeah, the only point was that it's not on the forwarding path, so it doesn't need fast memory. It only needs slow memory. Question?
Are you claiming that ISPs that use route reflectors are not running route reflectors, like traditional routers that are in the forwarding path?
I know at least a couple of ISPs that don't have the route reflectors on their forwarding path. I also know of an ISP where the route reflectors is on the forwarding path. So yes, that's not completely compatible with our model.
The common case is the latter.
Okay, but that being said, these could be actual PCs. So you could shift away from these machines being on the data path. So yes, there might be slight changes for some ISPs involved. Okay, and I guess that's the disadvantage here because it's slightly more invasive because it has the use of route reflectors. You need to reconfigure your external peerings, which is a cheat because I want it to be completely transparent to neighboring ISPs. On the other hand, the advantage here is that apart from shrinking the FIB, you shrink the RIB on all data plane routers. And again, the bottleneck there is not memory, but routing convergence, which I present evaluation results for.
Back up. I'm missing something
Sure.
fundamental here.
Yep.
So you divide the internet up into a subset of colors.
Mm-hmm.
You stick only the routes for one particular color in a router.
Yes.
Okay, now it's external facing. It gets a packet that's in some other section. What does it do with it?
Excellent question, which is my next slide. So I'll explain that. So I'll explain, because that's the thing I wanted to answer. Now routers only have partial information and how a packet's going to flow. In this case, packets come into a prefix in the red part of the address space to a blue edge router, and it doesn't know what to do with that. These packets are routed from ingress router I to aggregation point A, which is segment 1, and then from aggregation point A to external router X, which is segment 2. And I'll explain how both these segments work. When the packets come in, the blue ingress router doesn't have a route to the destination prefix. And so it somehow needs to know that these packets need to be sent to a close by red aggregation point, which in this case happens to be router A. To achieve this, in ViAggre, routers advertise the virtual prefix they're aggregating into the ISP's internal routing. So the two red routers advertise the red virtual prefix. And if you look at the forwarding table of the blue router, it contains routes for all the blue prefixes, and it contains one entry for every virtual prefix it is not aggregating. So this is how the blue router knows that these packets need to be sent to router A. Once the packets get there, router A has a route to the destination, and so it knows that the packets need to be forwarded to external router X. However, the packets can't be forwarded in the normal hop-by-hop fashion, because the routers along the path, the blue, the green, and the orange router don't have a route to the destination prefix. So they'll probably end up sending the packets back to router A, resulting in a routing loop. To avoid this, router A tunnels the packets. That is, it encapsulates the packets in an extra header such that intermediate routers only need to forward packets destined to external router X, which they can do normally. However, you can't tunnel the packets directly to the external router, because that would require cooperation from the neighboring ISP. Because the external router X is going to get these packets with an extra header, and it wouldn't know what to do with them. Hence, it is the egress router E that detunnels the packets. That is, it strips off the tunnel header before forwarding them onto the external router X. And all this can be achieved with standard router configuration. As a matter of fact, those of you who do VPN research might realize that the behavior of the egress router here is similar to the penultimate hop in an MPLS VPN scenario. And the important point to take away here is that we figured out a way to achieve all this with standard router configuration today. Question?
Step, the header includes in it the next hop, so that when E strips off the header, it knows that it's.
This is the next hop, and that's the trick. That's why E doesn't need to have the entire routing table, even though it's orange.
Operation on the line card?
Yes, it's doing on the line card.
It's not an exception case that has to go to the general processor.
No, that's what saves us. What saves us is the fact that tunnels have been adopted in mainstream networks for things like traffic engineering, and so most routers are equipped with line cards that can do tunneling at line card rates. And that's why the computational overhead is not high. And
this is a special kind of tunnel, right? It's tunnel plus this extra bit of information about the next hop.
So, as it turns out, existing MPLS tunnels have that sort of technology built in. So I'm just using standard MPLS technology, wherein the label that we use to identify a tunnel embeds this information of what the next hop is, and so there is no exception case. It's all on the data path, fast path. Okay? Question?
So basically, you change although you can reduce the routing table size, you change the network topology visible to every prefix, right?
Sure.
So how does it interact with traffic engineering inside of the ISP?
Excellent question. You are 2 slides ahead of me, and I'll address that point in a second. I'll get to that. Okay, question.
Product to the MTU since you added the extra header at the...
Excellent question. So tunnels represent two kinds of overhead. There is an overhead in terms of computational cost, which I just mentioned, and there is a storage overhead. As it turns out, and this is again a cop-out, because ISPs use tunnels for existing purposes, it turns out that layer 2 technologies and tunneling technologies have been designed in such a fashion that you don't have MTU issues. For instance, MPLS can work as a layer 2 technology. And even when you're tunneling, the MTUs have been designated in such a fashion that there is no IP fragmentation. If there were IP fragmentation, this would not work. Okay? Question, Albert.
An alternative would be to beef up the memory in some of the routers, so you don't have to tunnel to the red one, to tunnel to ones that know everything and have larger memory, and have a few of those.
Yes. So there is an entire design space wherein what I'm going to explain is this assumption that you don't want a lot of SRAM on any router. There are cases where you won't have, this router is just a new router, and so he can keep all the memory, and then you have these edge routers that rely on that specific router, and we have explored that in a little bit detail with engineers at Huawei. I'll comment on that very briefly at the end of the talk, and if you're interested, we can talk about that offline. Okay?
It makes a slight bit more failure sensitivity, right? You might have a path from I to E or I to X, but you might not have a path that goes through one of the red routers.
Excellent question, which is my next slide. Okay. So this basic design leads to a couple of design concerns, the first of which being failover. What happens when router A fails? Because there's a path that exists from external router to external router. If you remember, the blue router receives two routes to the red virtual prefix, one from A, other from A2. Hence, when router A fails, it installs the alternate route into its forwarding table, and the packets are rerouted automatically. So the point here is that failover in ViAggre happens automatically using existing mechanisms. And the ISP doesn't need to do anything fancy other than to ensure that there is some aggregation point to failover onto. And so you have this management overhead wherein you want to make sure that in order to get the same amount of qualitative robustness, you pick and choose your aggregation points properly. For instance, one way to do it would be to ensure that every POP has a couple of aggregation points. And so the robustness doesn't suffer much. And the important point here is that you don't need to do anything fancy other than to be smart about how you place the aggregation points.
The FIB would need to be re-updated, right?
So what happens here is that assuming a mesh of internal peerings, this guy already had two routes to the red virtual prefix in the RIB. And so essentially what he needs to do is send stuff from the RIB into the FIB, which in our measurements is sub-millisecond times.
He also has to get a failure notification that says A is dead.
So what happens is, assuming you have a mesh of peerings, your BGP peering session goes down. So if you're using aggressive timeouts there, you get that instantly, and you fall back onto the other option, put that into your FIB. And our measurements have shown that this is on actual hardware routers, that if you can configure that properly or engineer that properly, that comes out to be in the sub-millisecond range. Essentially detecting that your peering has gone down.
At least like a one-way latency, from
Yes, so one-way latency, well, so it turns out to be very small. Question?
One way to look at this is you're taking what was one router and distributing it into 4 other routers.
Yes, it's essentially, yeah.
Does the cost go up, but do you now have to buy 4 more routers, 4 times as many routers as you had in the past? I mean, what extra load does this put on the internal routing structure of this?
Excellent question, which is my next slide. So, as you mentioned, in its naive form, ViAggre requires traffic to be routed through an aggregation point, which, as people mentioned, can impose stretch on traffic. It can increase load across the ISP's routers and across the ISP's link. And I guess I'm not sure if I say this at some point in the slide, but the stretch answer is the fact that most ISPs are designed in the form of POPs, where you have a few routers in each POP, and you want to make sure that you divide the routing table within each POP, so you're not going from New York to Chicago. The load answer is slightly tricky. As it turns out, traffic on the internet follows a power law distribution. That is, 95% of traffic is destined to 5% of the prefixes. Hence, we propose that these popular prefixes should be loaded into the forwarding table of every router. This will ensure that a majority of traffic follows direct paths, a small fraction of traffic takes this detour. And so this substantially reduces the impact of ViAggre on the ISP's network. And this is what it makes ViAggre a good trade-off, the substantial reduction in FIB size while having minimal increase in load and stretch. And that's what the evaluation results are going to show. So unless there are questions at this point of time, I'll move on to the evaluation. Yes?
although some traffic the traffic volume to some prefix are small, it doesn't mean that those traffic are not important. For example, some traffic might be video. They are very big, but they are not very much latency sensitive. But some traffic like search are very, very interactive. If you going through this alternate paths, you introduce end-to-end delays.
That is very true. My argument that, well, for most of the traffic, things work well, and for a small fraction of traffic, things can go bad. If things can go really bad in some application-specific scenarios, this would not be acceptable to the ISPs. It might break SLAs, and you'll notice that I'll come to that in 4 slides from now. I'll address that issue in terms of how you want to assign the aggregation points, because you want to be smart about that. Yes?
When you said 95%, you mean 95% of the bytes, 95% of the what?
95% of the bytes.
Isn't bytes dominated by BitTorrent?
No, it wasn't. It used to be the case. It's not now. If you look at latest results, BitTorrent is pretty.
It's been held for 4 years, right? I mean, can you go back to one slide?
Yes, this is actually 10 years. Jennifer Reckford's papers in the late 90s. Even now, So what happens is that, for instance, I'm AT&T. I have 2 prefixes that belong to me that are my customers, and so a lot of traffic is going to them. There are 3-4 prefixes that belong to AOL and Comcast that are getting services from me, and their traffic is, again, AT&T local. So you have these 4 prefixes that are carrying about 40% of the traffic. What turns out is the rest of the traffic is essentially going to Google and Microsoft data centers that are, again, connected to AT&T. So it turns out any traffic coming from AOL, Comcast, and AT&T customers going to those data centers or peer-to-peer applications is AT&T local, which again belongs to these 10, 15, or 50, or 100 prefixes, which turn out to be popular. I actually was very confused about that point too. As in I came up, did this evaluation based on net4 records, and I was like, this doesn't make sense, and I have some insight into why that works, and I'd be happy to explain that to you offline. Okay? So, evaluation results. And I'll address that question of what happens for really bad cases. So, first up, evaluation metrics. When an ISP is choosing to deploy ViAggre, it is looking to shrink the FIB on its routers. On the other hand, the use of ViAggre imposes stretch on traffic, and it increases load across the ISP's routers. So there are positives and there are negatives. Further, ViAggre provides the ISP with a number of deployment options. And I listed 3 of these here. So the theme of the evaluation is going to be, how can the ISP use these deployment options to tune the positives and the negatives? And the main result that I'm going to try and show is that the positives far outweigh the negatives, which makes this a good trade-off. In the interest of time, in this talk, I'm going to focus on the latter 2 deployment options. Now, if you think about it, the choice of which routers aggregate a given virtual prefix is an important one. Because the more aggregation points you have, the less stretch you'll impose on traffic. On the other hand, the more aggregation points you have, the more cumulative FIB space you'll end up using. So there's a trade-off between FIB size and stretch. And the ISP can use its choice of aggregation points to tune this trade-off. In our work, we considered a simple constraint-based optimization problem, wherein the ISP is trying to minimize the worst-case FIB size across all its routers while constraining the worst-case stretch. Now, this is a simple constraint, but I still think that it's practically relevant and it answers your question because I want to make sure that my existing SLAs are not breached and my latency-sensitive traffic is not completely hosed. So I could say, well, even in the worst-case scenario, my stretch should not be more than 4 milliseconds or 5 milliseconds. And that's what the kind of exercise that an ISP can do, and you can get more sophisticated. On the other hand, the worst-case FIB size is important because that's what I need to provision for. As it turns out, this simple constraint problem can be mapped to the multi-commodity first relocation problem, which turns out to be NP hard and has been studied quite a bit in the theory community. As a matter of fact, there was a Soda paper in 2004 that proposed an approximation algorithm with logarithmic bounds for this problem. For our purpose, we implemented a simple greedy approximation algorithm. And we applied this to data from an actual tier 1 ISP on the internet. So we took the ISP's topology, their routing tables, their traffic matrix, and we assumed that the ISP wanted to deploy ViAggre and was using our tool to determine an allocation of aggregation points. The results for which are plotted on the graph here. So x-axis is constraint on worst case stretch, y-axis is FIB size. As you relax the constraint, the worst case FIB size drops. And with a constraint of about 4 milliseconds, you get a worst case FIB size across all the routers of around 10,000 prefix, which is 4% of the global routing table. On the same graph, on the right-hand side y-axis, I've plotted the actual stretch. And there are 2 points to note here. The worst case stretch, which is the dark blue line, is always less than the constraint. A good sanity check for the algorithm. While the average case stretch is pretty much negligible throughout, 0.2 milliseconds. So FIB size reduces, stretch increases, stretch is pretty much negligible throughout. Another way to look at this reduction in FIB size is to look at the extension in lifetime of routers due to the use of ViAggre.
I have a quick question.
Sure.
So what you're saying is that blue line, there's this imaginary x equals y line that it lies under.
Yes.
So that's the measured worst case stretch as opposed to the constraint that you solved for.
Yes.
Okay.
So that's the measured worst case stretch, and obviously you would want to make sure if your algorithm is working right, it's below that diagonal line. Right. Yes. Question?
The benefit on FIB size bottoms out at around 4%. What's the intuition for why it doesn't sort of keep coming down? What's
the intuition there is that we are limited by the smallest pop that this ISP had. So if this guy had a pop with 5 routers, I'm limited to dividing the routing table amongst those routers and then relying on some close by pops, but my stretch constraint ensures that I can't rely on some random pop far away.
Then about 5 reflects your choice of number of colors in your virtualization.
Yes.
So that was fixed for this.
Yes, it was fixed for this. Okay.
Wait, that I didn't understand. I didn't think that the number of colors was fixed. I thought you were saying that the stretch constraint forced the number of colors to be fixed because you didn't have more colors than that in one pop.
No, what I said was that in this exercise, I started off with a certain number of colors, let's say 200 colors. And then I said, yes, a decent number of colors, so that I get an even distribution of prefixes across these various colors. That's why I need a decent size, not 4 or 8 or something like that. Okay? And now, another way to look at this reduction in FIB size is to look at the extension on lifetime of routers due to the use of ViAggre. And we conducted a study to the effect, and the highlight of that study was the fact that ViAggre can be used to extend the lifetime of already outdated routers by 7 to 10 years, while imposing no stretch on the ISP's traffic, which I'm sure many ISPs would be very excited about. Now, in its naive form, ViAggre requires traffic to be routed through an aggregation point, which, as I mentioned, can impose load on the ISPs. Yep.
So this is a zero stretch.
I should have clarified. Zero stretch means that if you're taking a hop within the pop, that is 0.
Okay, within a pop.
Within a pop, and as it turns,
number of routers
within a pop. So I should have clarified.
So I was going to say, it didn't seem.
It's no magic.
Routers would be exactly the same routers you had before.
Yeah, sure. The only problem is that, well, you can still take a hop within the pop, but the load is a problem, which is. Yeah, in terms of stretch, they're okay. In terms of load, they're not okay. Right. And this is where the popular prefixes come from. Question?
7 to 10 years, assuming that the growth rate continues at the measured rate?
So there, I used 2 models of FIB growth rate. One was an exponential model proposed by Jeff Huston. One was a quadratic model proposed in some IETF document, a quadratic-based model. So yes, the people based on past growth have assumed extrapolated future growth, and I took 2 models, and based on that, I got this range. And of course, if IPv6 deployment takes off or IPv4 deaggregation takes, the growth might be more, in which case this number would reduce a little bit. Yes. Okay. So the load problem, and this is where popular prefixes comes in. We performed a pretty long-term and comprehensive study to determine the fraction of traffic carried by different percentage of prefixes. And the highlight of that result was the fact that a small fraction of prefixes carry a vast majority of traffic. This is what past results had shown. This is what we found. Hence, we proposed that these popular prefixes should be loaded into the forwarding table of every router. Given this use of popular prefixes, we conducted a load analysis to determine the increase in load across the ISP's routers. So, x-axis, percentage of popular prefixes, y-axis, increase quartiles for increase in load across the ISP's routers. As we increase the popular prefixes, load drops sharply. And with around 5% popular prefixes, we get a maximum load increase of 1.38%, which should be pretty acceptable. So hopefully, this quick set of results convinces you that ViAggre can be used by ISPs to extend the lifetime of their routers while imposing negligible traffic stretch and almost no increase in load across their routers. Beyond this, ViAggre has a number of other advantages. For instance, ISPs don't need to buy into the ViAggre model completely. They can play around with it on a limited scale so that they get comfortable. And there are several other advantages. Question?
So in your selection of the aggregation point, you only consider the stretch. Have you considered the load on the links?
So the simple optimization that I presented in this case, the idea there was put a constraint on the stretch, measure the load. Turns out that load is pretty small. Beyond that, obviously, for an ISP to deploy this, you won't want to constrain the stretch and load. I have a mathematical formulation of these constraints that I fed into an ILP solver, ilog. So essentially, I have a tool that takes these constraints and generates a deployment model that would satisfy those constraints. But the results in this talk are based on the simple constraint model. Yeah.
So the modeling you've done is with no failures of the routers. If you start taking, well, maybe I say this without knowing.
So what I'll present the failure model. The failure model I wanted to ensure was that if you are placing a color in a given pop, you want to make sure that there are two routers for that color. In that pop. Okay. Because, well, if that fails, you can rely on something on the same pop. Otherwise, you go to a some.
Then you won't affect stretch with any single failure.
Yes.
Right? Okay.
Yes. Right. That being said, you could come up with more complex constraints where you want to constrain the stretch even in the face of failure.
If you took a failure, would you have much worse long haul?
Question.
So I'll be impressed if you have a slide for this one. You've done previous work in denial of service attacks, and it looks like if I were a denial of service attacker, I could go after the layout of the routing and make sure that the load ended up just where I want it and make sure that things get dropped?
That's an excellent question. I don't have a slide for this, sorry. Essentially, as an attacker, what you want to do, and I'll answer this very briefly and we can have a discussion later, if you could send traffic to popular prefixes. That being said, ViAggre, when you have a packet destined to a prefix which is not popular, you're not relying on the control plane. So it's not as if you're taking a cache hit and getting something from the control plane. You're essentially forwarding it to some other router. Packets always stay on the data path. So that would ensure that no matter, well, not no matter, but for decent size attack traffic, you should be fine. And obviously, that can be accounted in how you deploy ViAggre. And I have some very preliminary results on that I'd be happy to share with you. Okay, not in this talk. So evaluation was fine, but there's a question that still remains unanswered. Question.
So I was actually expecting the pro slide to be followed by a constant, but you didn't see the target. So here is one question.
This is gonna be fun.
Research. So here is the question. There's one thing that's sort of, maybe it's not quantifiable, but it's the management overhead, right? There are already so many papers talking about routing configuration, how hard it is to keep them correct.
Yeah, how would you deploy this?
Excellent question. Which is my next slide. So we wanted a deployable system, and we went out and spoke to ISPs and operators, and there were two main concerns. First was, well, you're using all these control plane hacks, and what happens with installation time and convergence times and all those data plane metrics. The second, and perhaps the more important concern, was the management overhead. I went out and spoke to operators, and I was happy because I found a solution that's going to save the world, but they were concerned about the operational cost of this extra configuration. And having done some work on network management, I really appreciate that concern. Now, to answer these questions, we went out and deployed our system on a testbed of actual hardware routers at the Vail lab in Wisconsin. In the figure, I show a very simple topology, although we experimented with all kinds of bigger topologies. In the figure, we have an ISP that has deployed ViAggre, and it's exchanging routes with two neighboring ISPs, AS2 and AS3. We configured these routers to propagate routes using three different mechanisms, and I'll briefly recap them for you. First is status quo, which happens today. External router advertises routes to the edge router. Edge router forwards these using a mesh of internal peerings. Second, we have design one, wherein the internal routing setup remains exactly the same, except that routers use FIB suppression to only load the relevant routes into their FIB. We achieve this FIB suppression using something called access lists, which is a standard route filtering mechanism available on all routers. And the only thing that you need to know about access lists from this talk's point of view is that they can be massive due to the use of popular prefixes. Because if you have 1,000 popular prefixes, the access list need to enumerate them to tell the router that these need to go into the forwarding table. And finally, we have design 2, wherein external router advertises routes to a route reflector, and these are selectively forwarded. We achieve this selective forwarding using something called prefix lists, which is, again, a standard route filtering mechanism available on all routers, and these can be massive due to the use of popular prefixes. Now, we conducted a whole slew of experiments, and the one experiment that I'm going to focus on in this talk, what happened there was you tear down and you reestablish the peering between the external router and the edge router. And you measure the amount of time it takes for the routes to be re-advertised, installed into the edge router's FIB, and then forwarded onwards, something that we call installation time. The experiment had 2 key parameters. First is the number of routes being advertised by the external router, which in some sense represents the routing overhead, and the number of popular prefixes, which represents the size of the access list or the prefix list that you'll be using in the ViAggre deployment. And
whether you use Juniper or Cisco, right?
Yes. So these results are based on Cisco 7300s. I think we have experimented with Juniper routers too, M20s, I think, but the results that I'm going to show in this talk are based on Cisco router results, okay, which is shown here. So design 1 imposes substantial overhead in terms of installation time. And this increases dramatically as we increase the fraction of popular prefixes. This is because, as it turns out, routers today just aren't designed to deal with massive access lists. The overhead is too high, which is what I was alluding to at the beginning of the talk. So this is not a practical implementation, and we are still working on it. However, design 2 actually reduces installation time. This is because in design 2, the route reflector only needs to forward a subset of the routing table to the ISP's routers. As a contrast, with status quo, the edge router needs to advertise the entire routing table to the ISP's routers. And that's where that advantage is coming from. Further, the installation time doesn't increase much as we increase the fraction of popular prefixes. So this is great news, because this shows that not only are routers designed to deal well with massive prefix lists, but reducing the forwarding table can also help with internal routing convergence. So we started by focusing on FIB size, and it seems we can help with both RIB size on data plane routers and internal routing convergence, which is one of the advantages of reducing the RIB size. Question?
I don't have a good feeling for how many prefixes are often advertised within networks.
So,
where on the x-axis
so
is the
on the x-axis, we are here. So today, the internet routing table is around 280,000, 300,000 prefixes. So we are here, and we have done stuff here, and it turns out to be pretty same. Next is the management question.
What happens if the route reflector fails?
What happens if the route reflector fails? You need to be very careful about how you do the route reflector deployment, because all the external routers peer with them. But that is not any qualitatively different than what happens today, because today ISPs use redundancy to ensure that route reflector failure does not lead to route propagation failure, which is the same for ViAggre. Question?
Yeah.
Why the curves up? It's a log scale?
That's a log linear scale.
Sorry, I
My
should have
question is
pointed out.
exactly the opposite. Why is it so super linear? Because if you plotted that on a linear scale, it would look like that.
Yeah.
This curve?
Yeah. Those things are wickedly super linear.
This curve would increase. I don't have an answer to that question. I'll have to think about that. I guess it could be a function of, as you're increasing the number of routes, you're sending more data in, and things are getting congested. I don't have an answer to that question. I'll think about that, and I'll get back to you in a second. Okay, after the talk. The other question was the management overhead. Now, to address this concern, we went out to help with our deployment, developed a management tool that can help with the ViAggre configuration. It's a simple tool that takes an ISP's existing configuration files and the net flow records for the traffic statistics, and it generates configuration files that are ViAggre compliant. So effectively, you have an automated means to go from a status quo network to a ViAggre compliant network without any manual intervention. Of course, these scripts were specific to the Cisco 7300s we were using and the MPLS technology we were using, but their simplicity suggests that the configuration problem might not be insurmountable. That being said, it's an excellent question because we chose a configuration-only path for ViAggre because we thought it would lead to easier deployment, which is not necessarily true. And another way to approach the problem would be to assume router vendor support and to build all these primitives directly into the router, which is what we're working on with engineers at Huawei. So this would reduce the configuration burden on the ISPs, and it would make them more comfortable because they'd have router vendor support. So we have a couple of IETF drafts out on this, although I'd say this is more of a work in progress. So with that, I'm going to conclude the ViAggre component of the talk. ViAggre, or virtual aggregation, is a configuration-only approach to shrinking the FIB on ISP routers. ISPs today can use ViAggre to extend the lifetime of their installed router base. Of course, ISPs may need to upgrade their routers for other reasons, but at least their hand is not going to be forced by factors beyond their control, namely the growth in the internet routing table. Further, I don't think of ViAggre as a be-all and end-all solution to the routing scalability problem. Instead, I think of it as a simple yet effective technique to sort of hold the fort till a more clean state solution can come along and save the day. So that was ViAggre. And I have a few minutes left, and so I'd like to talk briefly about future directions. Question?
I'm sorry, I don't understand this argument. You just said that, this is a first step solution until a clean slate solution. But isn't the fact that the lack of clean slate solutions coming in is because we keep kind of patching? Isn't it kind of you prolonging the...
That's an excellent question. So Yes. So the thing is, if I were arguing for dirty slate solutions, where you come up with these dirty solutions and place band-aids on the network architecture, you'll never get to the clean state solution. And so as researchers, we have to be very smart about how you design the dirty slate solutions so that there is a clear progress path. In the context of ViAggre, the idea there is you convince ISPs to use this. They'll run into trouble, they'll management overhead and all those things. You'll get these changes implemented into routers. Once you have things implemented into routers, which is what the second step, and that's what we are currently pursuing, you can actually move to inter-domain ViAggre. Because if I'm an ISP, I have a routing table size problem. I can turn this switch off into my routers without any management overhead and get these advantages. So now you have various ISPs that have deployed ViAggre. And beyond that point, there would be incentives for them to cooperate to reduce the FIB size even more and to ensure that end-to-end latency does not suffer. So there is a clear progress path, at least for ViAggre, of why this is not a band-aid solution, but this would actually encourage our movement towards a clean slate solution, which I think I'm very proud of. Okay. Yep.
How widely are FIB caches used today?
FIB caches went out of flavor 10 years ago. And there were reasons for that. ISPs weren't happy because when there was a cache miss, you would have reduction in throughput and increase in loss. Vendors weren't happy because they couldn't benchmark their product. And that's why FIB caches went out of business. That being said, it's a very insightful observation because what I've designed is essentially a distributed caching system. So centralized caching, when you have a cache miss and you get stuff from the control plane, doesn't work in the 10 years ago, and it wouldn't work today. That being said, that's why you need the distributed caching system, and that's what ViAggre is.
So if you had routers today that did have FIB cache, did use the FIB as a cache, it seems that it would do some of what you're proposing in that, for the elephants or the most popular traffic, you would always hit in the FIB, and anything else, you go up to the router, and sure, you're going to take a hit, but maybe that hit would be smaller than a routing stretch hit.
That is exactly what we're doing with Huawei. You actually do this popular prefixes calculation online, you populate the FIB without any management overhead. If you do have to take a hit, you go onto some other line card instead of some other router. And so that's sort of the kind of things that we are exploring with.
So is that pretty much exactly the same as the old FIB cache stuff, or is there some new
There is some new stuff there, because old FIB cache stuff had to rely completely on the control plane. You're fetching data from the root processor. You don't want to do that because of reduction in throughput. You either want to rely on some other line card on the same router or some other router in the same POP. So there are some differences there. But the dynamic calculation of popular prefixes, what you just mentioned, is something that we are implementing in Huawei routers. Albert.
I was just thinking about the economics. So the ISPs will avoid upgrading line cards at their access router because there's lots of those line cards. But they wouldn't care about upgrading core routers. They do it every 3 years or so, and they don't even have to update all of them. in your scheme, just the ones that you relay through. So again, this brings me back to my question, why don't you buy a small number of core routers that know everything? Why do you need to partition by?
That's a good observation. So yes, there's one deployment model wherein you can buy some deployment core routers that have a lot of memory and you rely on them, and that leads to a simpler deployment model. And we have explored that a little bit. That being said, you brought up an interesting point when you said that, well, you need to upgrade routers every 3-4 years anyway because of data rates, core routers, because of data rates. And so why do you need to bother? Because the memory upgrades come along with the upgrade of the actual router, right?
Compared to the cost of the links, for most ISPs,
yes,
it's not going to be a big deal.
Yes. As it turns out, well, there's a separation between what happens for medium ISPs and large ISPs. Medium ISPs be tier 2, tier 3s. For medium ISPs, the concern is that they need medium links and medium routers, but they need big routing tables. As a contrast, big ISPs need big links and big routers and big routing tables. There's a mismatch there. That's where ViAggre helps. That being said, on the side of tier 1 ISPs or big ISPs, as far as my understanding goes, and please help me here, 5-10 years ago, every few years you change your router because you need new data rates. Data rates went up and you need to carry more traffic. Now, router line cards have reached lambda speeds, which in turn implies that most of the upgrades will come because of memory. And so it is going to hurt the bottom line of ISPs. Is it going to be an influential factor for ViAggre deployment? I don't know. But we can take that conversation offline. Question?
I have a specific question. You were talking about MPLS used to set up your tunnels.
Yes.
Would you have an estimate of how many MPLS tunnels you need to set up? Because it almost feels like for each
That's an excellent question. I never figured that somebody would get to that level of detail.
I'll tell you why I care about it. Because you were talking about routers that are 7 to 10 years old. And having talked to Cisco and folks like that, they have limits on how many MPLS tunnel ends can sit on routers. Especially the older routers don't support very many of them.
That is very true. In a naive deployment model, which I explained in this talk, you'd have tunnels equal to the number of directly connected external routers that you have in the deployment model that I showed. That being said, you can do an optimization wherein you only advertise tunnels for every edge router, which reduces the number of MPLS tunnels that you need to hold by an order of magnitude. So we are talking about 2,000, 1,000, 2,000 tunnels, or the number of routers that you have in the ISP's network, which can vary from 200 to 1,000 to 1,500. And as far as I know, at least the 3-4-year-old Cisco 7300s we were working with, they can support that many number of MPLS ISPs. So there is an optimization that goes from reducing the number of tunnels to 10,000, which is the number of directly connected routers to the ISP, to the number of edge routers, which is a direct function of what your topology looks like. Okay? Well, that was a good question. Well, I wanted to speak about future directions. I don't know how things work, because I'm supposed to, do I have 5 minutes? Okay, I'll try to keep this very brief. Okay. Throughout my graduate career, I focused on low-level networking problems. This has allowed me to delve deeply into one area so as to have most impact. I think I've been relatively successful at this, and it has led to a number of new ideas that I plan to pursue. Now, while there is a decent amount of work to be done in core internet research, I do believe that the field's best days are sort of behind it. And I say that with some amount of sadness. In this context, I think my past work is useful for 2 reasons. First, it taught me that good research can comprise of clean slate and dirty slate components. Second, it equipped me with the requisite tools to diversify my research beyond these core interests. And to give you a quick example, in one of my current projects, I'm building a system that facilitates the transfer of delay-tolerant bulk data. So this would be users downloading movies and software, but they don't necessarily need it immediately. And the insight here is to take advantage of this delay tolerance to reduce user cost and to improve performance. So this is an example of a project which is at the borderline of traditional networks and peer-to-peer systems and distributed systems. And so I'm already moving up the stack. Beyond this, my current pipeline of projects is a mixed bag, and I'd be happy to speak to you about these if people are interested. To put this all together, I want my research to be geared towards building network systems, both traditional and emerging that are better along several dimensions, including their scalability, their manageability, their reliability, and their security. Further, I want my research to retain this dual theme of instant and delayed gratification. And I'll explain what I mean by that. Given a problem space, I want my projects to track a specific roadmap, wherein the first part or the first step is to find the largest subset of the problem space that can be tackled without invasive changes. So this is the near-term solution that can help things today. Next, I would like to use insights from this solution to guide a more complete solution that most likely will be invasive in nature, which is the long-term solution that can help things eventually. In the context of past work, I have done work on clean slate and dirty slate projects. And the idea now is to sort of combine them and have a unifying thread going through them. And I'll give you a quick example. In a couple of my past projects, I've used tunnels in clever ways. For instance, in ViAggre, we use tunnels to shrink the FIB on ISP routers. I think tunneling is a very powerful primitive. And I'm actually surprised at how little attention tunnels have received in the research community, although that's slightly changing a little bit. For instance, I noticed that Dave and Albert have done Monson stuff where he used tunnels for load balancing and scalability. I think tunneling is a very powerful primitive. And I think that a properly designed and a cleverly incentivized interdomain tunnel architecture represents a very good opportunity to have genuine impact on many long-standing networking problems, like routing scalability and traffic engineering and load balancing and perhaps even network security. So this is an example where the same notion can be used in the near term to help things today, and it can be used in the long term to get to eventual solution. Note that I'm not claiming that these solutions will spur architectural change. All I'm saying is that when the severity of the problem justifies the cost of change, my solutions will have a better alignment of costs and benefits, and hence, I think, a better chance of deployment. And on that optimistic note, I think I'm going to conclude my talk. Thank you all for your patience. Thank you for having me here, and I'd be happy to answer questions.
Well, let's thank the speaker.
Yep.
So I think you've done a great job of actually showing how this solution actually has very good properties and it's easy to adopt into it. If you look back at all the work you've done, do you think any of it has had impact so far?
In terms of the older work, so the IP...
Give examples where your previous work has had impact, where kind of like, so...
Sure. That's a fair question because I will. So in terms of the Anycast stuff, I think it had some impact because I got to deploy my servers. These are 7 boxes that are actually advertising these prefixes, and people are interested in growing that deployment. Because for IP Anycast, and this is very technical, as I'm sure we can get this offline, for IP Anycast to actually compete with DNS-based Anycast, I need a substantial size deployment. I have 7 servers right now. And if I get to 20-25 servers, that would be a substantial enough deployment where other services, other research projects might be able to use my IP Anycast-based service instead of DNS-based Anycast for some advantages.
So when you say I have 7 servers, you mean you have a start? I mean, what do you mean you have 7 servers?
I have 7 servers in the sense I took used 7 Dell boxes and shipped them to different ISPs or labs that were interested in hosting my boxes. I went there, installed my server, spoke to their upstream ISP, installed a BGP peering, advertised my prefix, and installed my software on those machines, which is running right now. So as a graduate student, I think it's not as kind of an impact I would like to have, but given my persistence, I think I've been pretty happy with the kind of things I've been able to achieve. Albert.
So I know that the ViAggre work is...
Sorry about that.
is being pitched in a very active working group. They both have an IETF effort and an IRTG effort. There must be, a dozen proposals out there. So how are you doing? I mean, how is it stacked up, and what's the difference between your proposal and Tony Lee's proposal and the 6-to-1 and all that?
Sure. So there are a whole set of proposals that I mentioned that are clean slate in the sense that require changes to software and hardware. And yes, they are amazing proposals because they tackle the entire problem space, but they don't get enough traction. There is a second set of proposals that do not require substantial change to protocols, but they do require cooperation from router vendors. For instance, FIB compression. The problem there is that Cisco doesn't want to cooperate because it wants to sell more routers, which I can understand because they have their economic incentives. And the reason ViAggre, and this is me being optimistic or speculative, might just take off, and it's just getting some traction, is because there is a form of ViAggre that does not require any cooperation. If you're an ISP, you have a problem, you go out and deploy this. Obviously, there are some management concerns that we have a management tool to address, and if you wanted to, there could be a startup where they have a management solution and people might deploy ViAggre. And I think that is the only reason why there is some hope of this actually getting somewhere, some tracks, beyond some RFCs, it actually getting deployed in some networks, which is why I'm slightly pursuing that. Because it can be a lot of pain in terms of my time. And the only reason I'm pursuing that is that it's something I came up with, and I think there is some hope that this can help network problems in real. Question.
So I like the approach, but the way one of the slides was worded, which says that you would be able to increase the lifetime from 7 to 10 years from now. So there's this battle. I'm trying to understand whether we're trying to engineer software beyond the projected hardware reliability guarantees that could be provided for these routers anyways. Is there?
No, there are no projected reliability guarantees. The RAM works just fine. It's just that somebody else, I'm an ISP, you are, as a network operator, might be lazy and you're not doing your aggregation job and you're advertising 10,000 prefixes even though you're supposed to advertise 1,000 prefixes. And now I'm supposed to maintain all that in fast memory. And my router vendor won't help me because he wants me to buy new routers. And so as an ISP, I need some mechanism of being able to solve this problem, which is what ViAggre comes in. So I don't think it runs into problems of reliability. Yes, if you were, for instance, most ISPs, when they upgrade the routers, it's because, well, data rate went up and I have more customers, which is fine because at least you're getting more revenue. When you need to upgrade a router because of RAM constraints or routing table memory constraints, it's not because you're getting more revenue. Although I'd like to avoid the purely economic discussion because I'm not very good at that. Question.
This question comes up at the end of every talk, and in a sense we're trying to get generic insights, if you will. So what you've done essentially is add an extra layer of hierarchy to reduce the amount of state at the lower levels of hierarchy.
Yes.
There are multiple ways of doing this. Put a cache, put a distributed DHT to, I don't know, flat routing.
Sure.
Unique insights that we're missing in the talk.
There's no unique insight. That's essentially the insight. I came up with a distributed caching system or a level of indirection which tackles a pressing problem, and I figured out a way to achieve that without any changes to hardware and software. That's the key point. It's, yes, I have not come up with, I'm not going to get any big prize or something like that. It's more of I came up with a cool idea which there was a pressing problem for, and I came up with a way to achieve that without requiring any cooperation. Because as networking researchers, you have this constraint, and I'm sure you must have experienced this when you read in your papers, that you want to do cool, interesting work, but it's difficult to do cool, interesting work because there's all this legacy stuff out there. And the fact that I was able to do this cool solution in the context of legacy stuff is something that I really like.
So FIB suppression, building it out of tunnels, essentially making it work with the right infrastructure.
Making it with working with the right infrastructure, ensuring that it provides good trade-offs. Because it's, at a simple level, you have reduction in FIB size, but load goes up and stretch goes up. And so you want to make sure that you balance the right elements. And you want to make sure that the negatives are tiny enough that ISPs might be interested to take those costs, while the positives are high enough that ISPs might actually be willing to take the trouble of deploying these things.
So are you overly, I'm just going to hold back, but let me ask.
Oh, please.
Are you overly constraining yourself by the constraints that exist out there?
No, I'm not overly constraining. Yeah, please continue.
Because thematically you talked about that, which is I want to sort of work within parameters that are given to me, and I want to make sure that my solutions actually work within the parameters. And then sort of you talk about clean slate and dirty slate and all that stuff. Can you go back and tell me where you've actually done clean slate design?
Yes. This is the stuff that I had done on network management. I guess the slide is pretty close enough. Yeah, okay. So the idea there was network management is really hard. People here have done a lot of work on network management. And the idea there was that we distilled the reason why we thought network management was difficult. And we came up with this explanation that it's hard because today protocols and devices tend to expose too much information. If you look at the management interface or the MIB repositories, which is the management information base, it comprises of thousands of variables. And you need to build management applications that understand these variables.
Right?
Yes, the comments.
So I'm familiar with that. So the question is that, do you feel burned from that, or do you feel that that's just, do you feel like you didn't get enough out of it?
Yes. So there are pros and cons. I guess there's a positive side and a negative side. From a research point of view, I had a lot of fun in Conman. From a deployment point of view, I had a lot of fun because I was able to show that you take these protocols and you model them according to the Conman abstraction, and you get all these benefits. It was a lot of fun publishing this Conf paper and Infocom paper. What was not fun was going to Cisco and talking to actual engineers and them saying, it doesn't seem like we'll be interested in this in the next 5 years. So yes, you have to balance the trade-offs. That's what I was saying. Yes, there are cases where I would like to make sure that, I want this functionality to be provided in systems or the internet 10 years from now, or this problem to be solved. I want to distill the architectural reasons why that might be the case. I want to pursue where we'd like to be and come up with solutions like Conman. On the other hand, I would like to keep my engineer hat on and come up with solutions that can help with things today too. So I'm very happy with what Conman ended up with. So I didn't want to get an impression that, some work in the past that I'm not very proud of. I really enjoyed that a lot.
That's great.
Thank you. Thank you.